Welcome student to Radiation Oncology course. I am Dr. Ganesh Kumar Patel and today's lecture is the lecture number 38 and the topic of today's lecture is to quality assurance of LINAC part 2. So in continuation with the quality assurance of a LINAC, the quality assurance which we are going to discuss is the flatness and symmetry. As we have seen that the beam profile of a photon beam or an electron beam is flat beam, and this is perform a flattening filter. So look at the picture. It is very important to know that your beam should be flat. How do you verify? And how would you verify the beam is your symmetric? So there is a formula for the calculation of a flatness. You can see at the picture, and there is a formula for calculation of the symmetry, and here it is the picture of a flat beam of a 10 by 10 field size. So for consideration of dose, max dose and minimum dose, the 80% central area has to be considered, because beyond this the gradient started, and here in this gradient there is a sharp dose follow up and you cannot accurately identify your D max and D minimum. So to the central region of 80% area is need to be find out, in which the point of max dose and a point of minimum dose has to be chosen with the help of a software, and this is generally calculated by the software. There is a manual process also, that you can irradiate a film, then that film has to be scanned and analyzed with the help of software. But now presently there is a software which is directly measure this profile and give this value of flatness. And the tolerance limit for the flatness and symmetry is plus minus 3%. In case of symmetry, you have to divide the profile at the center. You need to measure the area at the left hand side and the area at the right hand side, insert the value in this formula, and you will find out your symmetry. This flatness and symmetry is obtained in terms of percentage, and the tolerance should be within plus minus 3%. So this is a very important dosimetric test of your LINAC, as well as of telecobalt. I forget to mention that the same test is used for a cobalt also. Now the machine calibration and commissioning. Calibration term is mean that it's in day to day your life. Suppose your watch is not following the standard time. What you do? You just see the standard time. You just move your watch screw and adjust your time with your standard time, and that is called a calibration. This is a simple process of calibration. Similarly, this therapeutic equipment required a calibration at the time of commissioning. It means that they should know that what should be the standard value of dose at a particular depth. So that process is called calibration. Like in previous lecture, we know that the absolute dose at D max should be 1 centigrade per 1 mu. So this is a standard value. So you need to calibrate a machine in the beginning when the machine is new. When the machine is first time installed, at that time you need to inform the machine, or you need to record in the machine that your output should be 1 centigrade per 1 mu at the D max. That is called a calibration. And what is meant by commissioning? Commissioning is an important process which is performed once in a life of a machine when it is getting installed in a new radiotherapy setup. This is a process where a medical physicist is just create a brain of a machine, because machine comes with an empty mind. Machine don't know what amount of dose should deliver at what amount of depth, what amount of depth. For generating such a depth dose distribution, machine needs to trained, or machine needs to give it input data. That input data generation process is called the commissioning of a machine. In this input data process, you need a dedicated and sophisticated device that we call a radiation frequency analyzer. And this radiation frequency analyzer is generally used in your monthly quality assurance test as well as your annual quality assurance test for the measurements of various dosimetric parameters like we have seen the flatness and symmetry. So there are two types of RFA. There is a one-dimensional RFA and three-dimensional RFA. In the beginning, there was the availability of a one-dimensional RFA. In one-dimensional RFA, there is only one axis of movement. It means that whenever you set a chamber can move vertically or chamber can move horizontally in a one direction only. That is why it is called a one dimensional. But with the evaluation of the technology, the RFA is also evolved, and there is a three direction movement. Simultaneously movement in a three direction can be possible with the help in this 3D RFA, means chamber can move simultaneously here, here, here and depth. So chamber can take any coordinate at any point of time with the movement, which was not possible with the 1D RFA. What this 3D RFA perform? 3D RFA perform the measurements of percentage depth dose, then beam profiles, cross plane, in plane profiles, then wedge PDD, then your output factors, then your diagonal profiles, and these all kind of measurements combined form a input data which are required to feed into the treatment planning system for the calculations. So you look at the picture. These are the picture of a beam profiles at different field size. Like this is a 2x2, 3x3, 4x4, 5x5, 10x10. These are the beam profile pictures of a different field size, and the beam profile picture at different depth. Like you can see that 1.4 means D max, 5 cm, 10 cm, 20 cm, 30 cm. So in this commissioning process, you need to measure the beam profiles for different field size, from smaller field sizes to the larger field size. In case of linear accelerator, the largest field size is the 40x40 and the smallest field size is the 1x1 centimeter. So in this way you have to measure the beam profiles for all these field sizes and at different depths. Similarly, you have to measure the percentage depth dose, means that up to the 35 centimeter of depth from the surface of a water to the 35 centimeter of a depth, the chamber move continuously from 0 depth to 35 centimeter depth and starts accumulating a dose, and it gives us this percentage depth dose curve for different field sizes. For different field sizes, for profiles, chambers move in this direction and performs this direction and gives you a flat beam. It gives you a flat beam. Okay. Now we understood the quality assurance of a flat beam, but it is not the beam which is available. There are the unflattened beam also there. It means that when you remove a flattening filter from the head of a gantry, you can give you will get a beam profile like this. You will get a beam profile like this. And as I explained during my lecture of SRS SRT, the benefits of a triple F beam or unflat beam is that high dose rate. High dose rate, it means that beam dose is delivered in a shorter duration of time. So the benefit of this triple F is especially for SRS, SRT and SBRT techniques. So here there is a no flat beam. So what we see in an unflat beam? So unflat, first we will understand this beam profile is as we have seen that in our flatness symmetry previous test, we were considering 10x10 field size for the measurement of flatness symmetry. In case of unflat beam, the beam profile should be measured for 20x20 centimeter field size with collimator setting and at 10 centimeter depth in a source to axis distance for all available unflat energies. Presently there are 10 triple F and 6 triple F availables. Now you can see that this is the picture. In this profile, the measurement of penumbra is a part of quality assurance. In this, for measurement of a quality assurance, you need to create an inflection point, means the point of a sharpest dose follow-up. For finding out the inflection point, you need to draw a tangent. You can see that here tangent has been drawn. And when you draw a tangent, the where this tangent is intersecting, here it is intersecting, here it is intersecting, here it is intersecting, here it is intersecting. You need to mark the intersection start and end. Then you need to draw a perpendicular line, okay, and that is called h value. The h by 2, at h by 2 you have to draw a horizontal line, and you will get a inflection point, right inflection point and left inflection point, and this line is called a reference dose value. We call it as a reference dose value. So for determining penumbra, a dose value at inflection point shall be taken as a reference dose value, RDV. Point P and PB, which are located at 1.6 and 0.4 times of RDV respectively, 1.6 and 0.4 RDV will be your PA and PB, that will become your PA and PB. On either side of the profile will be the measure of penumbra. Now this you will draw a perpendicular at PA and you will draw a perpendicular at PB, and this distance will become your penumbra. This distance will become penumbra of this side. Like similarly PA, you need to draw a perpendicular line, then here perpendicular, and this will become your penumbra. So for unflat beam, this is a quality assurance for penumbra measurement. Now you can look at this picture. This is the measurement performed by me. Here I have done everything manually. You can see that I have created inflection point left, right. If the RDB value is 43%, then you need to multiply with 1.6. You will get this value 68.8%, 70.2. Then draw a horizontal line. You will get a PA and PB, and you will get here penumbra. Similarly, the other parameters which required to measure as a part of quality assurance in an unflat beam is the degree of unflatness. That degree of unflatness is used by the parameter of 90%, 75% and 60%. You can see here degree of unflatness. The distance between these points 90%. You can see that here 10%, 20%, 30%, these are the 40%, 50%, 60%, 70%, 80%, 90%. So at 90% you have to draw a horizontal line and you need to measure a distance. You need to, at 75% measure a distance, at 60% measure a distance. The values of this, to quantify the degree of unflatness, the lateral distance from the central axis at 90%, 75%, 60%, those points on either side of the beam profile shall be recorded along the major axis of the available photon beam energies. Okay, and symmetry should be evaluated following the symmetry is the same which you measured in case of your flat beam. Measurement of off-axis ratio, this is the additional quality assurance. Off-axis ratio need to be measured. What is this off-axis ratio? From the central axis at a distance of 3 centimeter and at a distance of -3 centimeter and at a depth of 10 centimeter, chamber is placed at 10 centimeter depth. Laterally at 3 + 3 centimeter, you need to collect a charge. At laterally -3 centimeter, you need to collect a charge, and it is the ratio of the dose at the central axis. So the ratio of dose at central axis versus this, you will get a off-axis ratio, and the tolerance for off-axis ratio is ±2%. Then you need to create a table. Here you have to define a collimator setting like 20 by 20. Separation between inflection point. The tolerance limits for symmetry is ±2 mm. Symmetry ±2%, and for this degree of unflatness, the tolerance is ±2 mm. Means whatever the distance you are getting for R90, this X90, X70 by 60, it should not be more than ±2 mm from the standard value, which is called a baseline values. And your penumbra should not vary more than ±2 mm from the standard value or baseline value. Okay. Then the next important thing is that the next important quality assurance is that the patient specific quality assurance test. This is only the quality assurance which is dedicated to the individual patient. All previous quality assurances which we learned is the quality assurance which is in common for the whole equipment, and which is performed for to quantify the complete machine. But here the number of patients you are treating with an advanced treatment technique like IMRT, VMAT, you need to perform a quality assurance for each individual patient. This quality assurance test is not for a 3D CRT technique. This is specially designed test for QA test for a advanced treatment technique like IMRT, VMAT and SRS, SRT. What happened in this test and what kind of QA devices are used? In this, there is again a specialized device is there, that is called, this is a QA device of manufacturer PTW. There are some other manufacturers also like IBA, Sun Nuclear, but for example we have considered here the name of this device is a Octavius 4D. It is a cylindrical structure in which there is a cavity is there where you can put this detector inside this cavity and you can switch on the beam, and as if you are, it is a VMAT technique, if it is a rapid arc technique, as the gantry moves, this cylinder also start moving in sync with the gantry rotation. So it is synchronized with the gantry rotation, and as the gantry moves it also start rotating with the gantry. And if it is a IMRT, it is remains static. It remains static, and at from different gantries the beam is delivered, and dose is getting recorded in these detectors, and this is called a detector array. This detector array consists of 1024 or in this 760 in some, there are 760 detectors here. With advanced there are 1024 detectors or more with spacing of 5 mm. Detector to detector spacing is 5 mm or less between the detectors, depends upon the detector array. And detector can be different types like ion chamber with volume less than 0.05 cc or a diode detectors. Higher the number of detectors, higher is the resolution. So as I said, a higher number of detectors means the higher resolution, but higher is the cost of the device. So what happened in a patient specific quality assurance? For understanding this test, we need to understand when in treatment planning system a patient plan has been approved by a radiation oncologist and it is ready for the treatment with that plan. We need to create we need to create a quality assurance plan keeping the same parameters of the existing plan. There is no change in any single parameter of an existing plan. Only the thing is that this new created plan will going to be delivered on this phantom. The previous the approved plan was for the patient, and dose distribution you seen is in the patient, but in a quality assurance plan your dose distribution is going to be created in a phantom. So this phantom has to be scanned and insert into a TPS, and the plan with keeping all same parameters, that plan has to be copied over this phantom and has to be calculated dose, and this plan need to export this plan is need to be export in a analysis software, and your approved plan has to be delivered on a machine in a quality assurance plan. So it means that once the plan is exported into the control console, that plan will be scheduled for the treatment, and when it is scheduled for the treatment there is a one option called a QA mode. So that plan will be delivered in a QA mode. It means that the dose will not be recorded for the patient, but the dose will be recorded for the quality assurance purpose. And you need to install this device or place make a setup of device at the couch of a gantry, and with proper setup of this phantom you need to deliver a plan, means switch on the beam on, and the gantry will rotate and deliver a dose to this phantom. So once the phantom receives this dose distribution, it will create a dose distribution. That dose distribution you can see in the picture, that dose distribution needs to correlate with the dose distribution of actual plan. So what is happening here, there are two dose distribution. The one dose distribution which is planned for the patient, and the one dose distribution which is delivered keeping all the parameters of approved plan on a phantom, because we cannot perform this test on a patient for the safety point of view. So we are performing with the patient equivalent material, that is a phantom. Now in this case what happened, if this is the actual planned dose and this is our delivered dose or a measured dose, this dose distribution should coincide with certain certain evaluation tool that we call a gamma tool or a gamma index. This is the gamma index is a parameter which verify these two dose distributions. Now you can look at this picture. These two plans when correlated or coincide with each other, the plan is passed with 98.9%. So it means that your photon fluence dose distribution of both the plans is almost matched with 98.9% and the QAT is passed. The actual passing criteria. Now a verification, the difference between the actual delivered plan on phantom and verification plan relative to the accepted tolerance is indicated by quality measurement called a gamma index. As I said, this is a very useful in the quantification and comparison of two-dimensional and three-dimensional dose data where direct measurement remains challenging. How to evaluate this gamma index? It is evaluated using these two parameters, the dose difference and the distance to agreement have been reported in literature based on the selected current clinical standards of plus minus 3% and plus minus 3 mm are widely considered acceptable for photon beams. A 90 or 95% passing rate with 3 mm or 3% gamma analysis are suggested by TG119 following institutions. So this is the specific QA for the individual patient. Now the radiation survey. We already learned how to perform a radiation survey in case of telecobalt machine. The radiation survey for a high energy linear accelerator have a change, because in high energy linear accelerator there are multiple energies with energies higher than 10 MV. There is a production of neutrons takes place. When the energy, because of the pair production, the neutrons gets produced with energy 10 MV or more than 10 MV. In this case, an additional detector, we have seen this radiation survey detectors, which is ion chamber based detectors. An additional detector that is called a neutron survey meter. Neutron survey meter, you look at this picture, this is a picture of a neutron survey meter, is used for the radiation survey of neutron leakage of a linear accelerator bunker. So this is a layout picture. You can see that this is a linear bunker for a 6 and 15 MB linear accelerator. This is the isocenter, primary wall, and these are the points. Like in cobalt we have indicated the points, door D1, door D2. This is a console, this is other area. Here are the points, and similarly we have to create a table. And this is the way you need to report to the ARB of a radiation survey. You can look at the picture. Here you have to mention the energy for which you are performing a radiation survey. Then you need to measure. I said you that maximum field size in case of linear accelerator, maximum field size is 40 into 40, and with maximum dose rate, if the radiation unit in which you are measuring, generally MR per hour or micro hour per hour, then here you have to write down the maximum radiation level of your whole survey for that particular energy. If energy is greater than 10 MV, I said that the neutron, the same table has been created for the neutrons. In this case also same procedure at 4 different gantry angles, with primary wall, without phantom, with phantom, ceiling without phantom, door location with phantom, console, and in this waiting area. In this way you need to report your radiation survey unit readings and need to submit to the regulatory body. Then source on position leakage. As I said that similarly what happened in case of telecobalt, source is in the shielding, but there is a possibility that in shielding there can be a inherent leakage, means there cannot be a perfect shielding of a source. So whenever the radiation is getting strike with other parts of a gantry, there is a possibility of production of photons which act as a secondary particles, and in terms we called it as a leakage radiation. So first we going to understand what is the source on position leakage. This is a in-patient plane leakage measurement. In-patient plane, it means that your gantry is either at 0 degree or 180 degree and its couch is at 0 degree. This is called in-patient plane leakage. In this case, this is generally 20 to 24 point measurement. From the ISO center, you need to draw a radius of R1 and R2 with a diameter of 1 meter and diameter of 2 meter. And you can see at the picture, at 0 degree gantry, there are the two radius drawn, 3 radius are drawn, but generally we measure at 1 meter and 2 meter. And you need to, now the collimator is closed completely and it is covered with 2/10 value lead shielding. So collimator is completely closed, and again you need to put a 2 TVL thickness shielding below this field. The ion chamber is positioned at any one of the location at 1 meter or 2 meter. These are the different locations. You can see number, has been number 1, 2, 3, 4. So all these points you need to one by one either put a ionization chamber or either put a radiation survey meter. If you are using a ionization chamber for source on position leakage, you need to connect with the electrometer and you need to measure with the charge, and then you need to calculate. But in radiation survey, if you are putting a radiation survey meter, you can see the readings directly with the help of CCTV camera once, and every time you have to put your ionization detector or ionization this survey meter at these points and make a reading. Once you make a reading, that readings need to be divided with the value with the at 10 by 10 field size, the dose you are getting. So it is the ratio of a dose which you are getting with an open 10 by 10 field size at ISO center, and the dose with shielding of 2 TVL, complete collimator jaws closed, and ratio of the dose at these points. So when you will ratio and multiply with 100, your percentage of leakage should be 0.2%. Should be 0.2%. So this is the source on position leakage measurement. Now, other than patient plane leakage, it means that in this other than patient plane means that the plane where patient is getting treated is called, means because patient is generally lie on the couch, and couch can rotate up to 90 degree, and 0 to other, and the points which are not lying in the area of couch is called other than patient plane measurement. In this we generally gantry at 180 degree, and these are the points where you do the measurements for other than patient plane leakage measurement. This other than patient plane leakage measurement is performed for photon beam as well as photon beam leakage as well as neutron leakage. So in this maximum photon leakage radiation through beam limiting device like a collimator, the limit is maximum 2% tolerance limit, and average photon leakage through beam limiting device means through X and Y jaws should be 0.75%. Maximum photon leakage radiation through when MLC of either place jaws with replaced with MLC. So what happened in case of Elekta machines, the jaws are secondary jaws are replaced with MLCs, means there is a combination with jaws and MLC. In that case, the tolerance limit is 2% for maximum, and average is 0.75%. And when photon leakage radiation through MLC, when MLC is used as a tertiary jaw, this is a case of a variant machine where MLC other than X and Y jaws, MLC is used at tertiary position, and the limit is maximum, that is 5%, and maximum photon leakage in patient planes which I have seen 0.2%, average is 0.1%, maximum neutron in this leakage is 0.05%, my average neutron leakage radiation in the patient plane is 0.02%, and percentage photon leakage at 1 meter from the target is 0.5%. So these are the simple leakage measurements, tolerance limits. Then the MV imaging QA, because we generally perform a 2D imaging, it is available with every linear accelerator. It is necessary to understand what is the MV imaging QA. So it is important to understand the positional accuracy of a MV imager. Your MV imager should have a positional accuracy of less than or equal to 1 mm. Then coincidence of center imaging and isocenter means because there is a isocenter of MV isocenter is there, that isocenter verification should also within a plus minus 1 mm. Geometric distortion, the distortion which is generally happen in the image should be within plus minus 1 mm, and the spatial resolution of high contrast and spatial resolution of low contrast, which is being performed by a Las Vegas phantom. You can see at the right hand side, this is a Las Vegas phantom with a different diameter circles embedded in a metal piece with high-end material. Okay, so for this test tool is specially designed for high contrast and low contrast resolution. Then uniformity and noise, this is another test. Accuracy of HU values and constancy of HU values. So these are the MV imaging QA which are generally required to perform in a linear accelerator. There are other imaging QA which we will discuss in our next lecture of simulator SimCity simulator QA. Thank you very much.